Mhm.
Okay, so Poisson process. We're starting with what we call Poisson process today. I hope you know what the Poisson distribution is. You know the probability mass function of the Poisson distribution. Okay, so we have the stochastic process. That's NT, N of T, is defined on the state space S, which is from 0 to infinity, 0, 1, 2, 3 to infinity, where the probability that n is equal to n is given by this Poisson distribution. Is the number of events which occur in the time interval from 0 to t. So we are dealing with the number of events that occur within a certain time interval. Maybe we can talk about how many and the rate at which people are joining our conversation here, or the rate at which a certain event is occurring within a certain time frame. So Poisson process has to do with the number of occurrence based on certain conditions within a certain time frame. So we say that process is also a stochastic process. So the n of t, this n of t is referring to the number of events which occur in the time interval 0 to t. For a positive lambda, for a positive constant lambda, as d of t, the small time frame, as d of t, as it approaches 0, these conditions must be satisfied. So first of all, the probability that only one event occur in the time interval dt is given by lambda dt plus little o of dt. I will explain these things as we move on. And the probability that no event occur between that time interval is given by 1 minus lambda dt. And the probability that more than one event occur within the time interval dt is little o of dt, where this is a function of dt such that when you divide that function by dt, as dt approaches 0, this will be equal to 0. We call this little o of dt. So we say that nt has independent stationary increment with initial condition n of 0 equal to 0. So we assume that at the beginning of the process, there was nothing has happened. That's n of 0 is equal to 0. So we are going to show this. This proof is in my book, but I said this one as a past question some years back, so I want us to look at it. We call this one differential difference equations, and we are going to show that the differential difference equation is given by these two equations, where P of n is the probability that n, the number of events is equal to n, given that initially there was no event. N here is the number of events that also occur within a time interval from 0 to t. So we are also supposed to show that by induction that the probability that n event take place within the time interval 0 to t is given by this Poisson distribution equation. Are we okay? Do you understand what I've taught so far? Today you'll be enjoying my class because there are a lot of equations to study. Good. So we go back to the beginning. What do you mean by a Poisson process? A Poisson process usually record the number of events which occur within a certain time frame. Let's say you stand at your junction and or maybe on the N1 highway, and you have to observe how many accidents takes place in every week. I get how many accidents occur every week. So you are doing that count. That count is likely to be a Poisson distribution, follow a Poisson distribution. So Poisson distribution, Poisson process always have to do with number of events occurring within a certain time frame. Number of events occurring within a certain time frame. Are you okay? But this number of events, we assume that two events cannot occur simultaneously. That's where this first equation is trying to tell you. There's only one event that can occur at a particular time point. So we assume that no two accidents occur at the same time. You see, the occurrence happen one at a time. For instance, if I'm having a class and students are entering, and I ask, let's say, Freeman, record for me how many students enter into the classroom every minute. Every minute record how many students enter, or every 1 hour record how many students enter into the classroom. The number of students entering within a certain time frame, that number is likely to be a Poisson distribution. That number is likely to be a Poisson distribution. And it must be based on a certain condition. The condition is that we assume that two students cannot enter the classroom at the same time. So we assume that each student enter at different time points. The time may be close, but we assume that they don't enter at the same time, or two or three students do not enter at the same time. So the first condition here is saying that at any point in time, only one student can enter at any point in time. No two students can enter at a particular point in time. And the probability that no student will enter at a particular point in time is 1 minus lambda delta t. And the probability that more than one will enter at the same time is little o of delta t. So little o behave like 0. When you say little o, it behaves like 0 so what it means is that it's not possible for any two students, more than one student to enter into the classroom. That is, if you are using the student entering into a particular classroom as an example. You can also talk about the number of patients that's going to see a particular doctor, the number of patients that are waiting to see a particular doctor at any time. You can talk about that. These are all Poisson processes. So first of all, two students cannot enter. Let's say two events cannot occur at the same time, at the same time point. The event occur one after the other. That's the assumption for the Poisson. And it's possible that for a particular time point, no event will occur. But it is not possible for two or more events to occur at the same time. That's the last condition. So these are the three assumptions, but they have been stated here mathematically in terms of probability. I hope you are okay. So
Yes.
we are going to start with this thing. First of all, the question says show that for this process, the differential difference equations are given by these two equations, where P of n is the probability that the number of events taking place from 0 to the time t is n. And at the time 0, we assume that there's no event taking place at time 0. And we are also supposed to show that the P of n of t the P of n of t is given by this Poisson distribution. So we start with the proof. So the proof looks a bit mathematical. So if you don't like mathematics, you never like the proof. But any proof at all I prove for you is also a possible examination question. If I don't prove it, then it's not likely it will come. But once I prove it for you, it means a possible examination question. But the proof here is purely mathematics. So maybe the mathematics guys, they understand better than the economics people. Praise, are you doing mathematics?
No, economics.
Okay, economics. Okay. But what about Freeman?
Mathematics.
The other Freeman, has he joined? The other Freeman, what's the name?
Jeffrey, no.
He hasn't joined.
No, please.
Okay. So first we say let P of n be the probability that the number of events occurring at between the time 0 to t is equal to n, given that initially there was no event. Given that initially there's no event. So when you see this probability, P of n t, it means that is a probability that the number of events occurring between the time frame 0 to t is n, given that initially there was no event. At time 0. So we define P of t plus dt as, so there are 3 categories. When you look at the previous screen, we can divide this probability into 3 categories. That the probability that only one event occur, the probability that no event occur, and the probability that more than one event occur. So the probability of t at time t plus dt is given by this. That first of all, we assume that there was no event. If there's no event occur between the time frame dt, then it means this minus this will be 0. And the number of events will still be n. If you have n event and no event occur, then the number of events will remain n. Have you seen it? So times the probability that there's no event occurring. Then the second equation here is a probability that one event occur. Have you seen it? If one event occur, then the number of events here will be n minus 1. Probability that one event occur. So then the times the probability that more than one, R is 2 or more than one event occur. So this last part of equation 1, this aspect can be expressed as this. And because for more than one event, the probability is a little o of a, it means that this event for more than one, that's R equal to 2 or more, it will be equal to little o of a. Have you seen it? So the equation 1, in equation 1, when you look at equation 1, this is equal to that, this is equal to that, and the latter part of it is equal to little o of a. So you can write equation 1 here as equation 2, 3, 4 into 1. We have these equations. So we have P multiplying this, P of n, multiplying this, P of n minus 1, multiplying that, then plus little o of a. I hope you are understanding me. Then what we are going to do now is to take this Pn of t to this side, so it will come and subtract. Then when it's subtract, we divide through by delta t. We divide through this equation by delta t to obtain this equation. So this is like the first derivative when they are doing differentiation, the first derivative. So you are going to find the limit as delta t approaches 0. So the limit as delta t approaches 0, that's what we call dp dt. That's first derivative differentiation. So as delta t approaches 0,
Approaches
as delta t approaches infinity,
infinity.
yeah, as delta t approaches infinity, this will remain because there's no delta t here. And as this also will remain. But as delta t approaches infinity, this side will be approaching 0. This one will be approaching 0. As delta t approaches infinity, this one will approach 0. So that's why that term disappear here. So therefore, from this, by this differentiation, we have dp dt plus, that I took this one to this side, dp dt plus this will be equal to that. So this is a differential equation. For those who have done differential equation, so we are going to solve this differential equation. And that's all that you want to do. You want to solve this differential equation and find an expression for Pn of t. You want to find an expression for Pn of t. So this is, I think, the first level differential equation. For the mathematics guy, I'm sure this will be cool. Okay.
Yes.
So
Okay.
we are going to solve this differential equation to obtain Pn of t. So we move to the next level. And that is A. That answers the question A. You remember the question A? The question A says we should show that this.
By induction.
Yes. No, not the B. We'll come to the B. We are going to solve the differential equation using induction. But first of all, the A part of the question says that you show that this is equal to that. And also at the initial point, this is equal to that. So that's exactly what we have done. So we've been able to show by equation 5 here that the differential difference equation is equal to this. Wow. So it is understood that at n is equal to 0, when n is equal to 0 in equation 5, when n is equal to 0, in equation 5, when you put n is equal to 0 in this equation, wherever you see n, you put 0. This place will be -1. You know that. So we obtain this expression, p -1. The p -1 is 0. It does not exist. Thus, when n is equal to 0, we obtain this. When n is equal to 0, we obtain this equation. So these are the two equations we have to show for the A part. And for the B part, we are supposed to solve the differential equation. What is the time?
2:42.
It's 2:42.
And why is it telling my meeting will end in 10 minutes? I see. Okay. So we solve this equation.
As you said, maybe is this the free period?
No, I'm using the license one, so I'm surprised. Maybe it has moved into the, how do you call it? Otherwise, I cannot even schedule a meeting for 2 hours if it's the basic one.
Yes.
But this one, I was able to schedule a meeting for 2 hours, which means it's not a free one.
You find it.
Okay, so let's move on and make sure that you don't talk. When you talk, it's being recorded. So we have this equation. So we are going to solve for this differential equation. We are going to solve for this differential equation. From when P, for this equation 6, we can write it in this form. That's, we'll divide through by P of naught to get this form. Then we'll integrate both sides to get this integration. So when you integrate 1 over P, it will give you ln P. And this one will give you lambda T plus C. So that will be from the equation 6. And from equation 5, so we get lambda T plus C. So since n of naught is equal to 0, it follows that P of naught is equal to 1. Therefore, ln 1 is equal to C. So it is shown that C is equal to 0. So we put C to be equal to 0 here. So the equation will be ln P equal to minus lambda T. But we want to make P of naught the subject. So this will be equal to ln P of naught equals to negative lambda P. So when you take the exponent here, this will be P of naught to be equal to exponent e raised to the power negative lambda P. Have you seen it? So when you take the exponent here, it will raise this one to a power. Meanwhile, C is 0. So this will be e raised to the power negative lambda T. Good. Which can be written in this form. So it's e raised to the power negative lambda T, which can be written in this form. So it means it is true, that equation there is true when n is equal to 0. It gives you lambda T raised to the power 0, which is 1, e raised to the power minus lambda T over 10 factorial. Are we okay?
0.
Over 0 factorial, which is also 1. Okay? So we are doing it by induction. I hope you've all done proof by induction before. So first of all, it is true when n is equal to 0. Then we assume that it is true when n is equal for n. We assume
Yes, sir.
it's true for n. So this is true when n is equal to 0. So we first of all have to solve this equation. We have to solve this differential equation, this one, equation 5. So that's what we are going to do now. So we solve that differential equation. But to solve differential equation, the first level, you always need what you call the integration factor. So here the integrating factor is e raised to the power lambda T. So we multiply both sides of equation 5 by e raised to the power lambda T. We obtain this equation. So the left-hand side of this equation can be written in this form. It means when you differentiate this, you get this. So the left-hand side can be written in this form, where we multiply through by dt, then we obtain the equation 8 over here. So we have P of n e raised to the power lambda T equals to the right-hand side of equation 8. So first of all, we assume that the expression, the equation 8 is true for n equals to k. If it is true for n is equal to k, where k is a non-integer, then it means we can write pk in this form if we assume. So we wish to show that if it is true for n is equal to k, then it is equally true for n equals to k plus 1. So we wish to show that the expression is also true for n is equal to k plus 1. Okay, so equation 8 can be expressed in this form. If it's true for k plus 1, we can express it in this form, for which we can write this expression in the form of this. Please, are you okay? because we're told that it is true for K. So if it is true for K, then we'll replace P of KT. P of KT, and we'll replace it by this equation. Have you seen it? Because we assume it is true for N is equal to K. So this will be it. Then we factorize all the constants out. Then we left with this in the integration, under the integration, which when you integrate, you get what? K plus T raised to the power K plus 1 over K plus 1. So we have denominator as K plus 1 factorial times K plus 1, which is the same as K plus 1 factorial. K plus 1 times K factorial is equal to K plus 1 factorial. So the denominator becomes K plus 1 factorial. So we have shown that the equation is also true for K plus 1. So therefore, by induction, it has been shown that P of N, the probability that in the interval 0 to T, N event occur in the interval 0 to T, N event occur is given by this Poisson distribution. I don't know if you get it. Where lambda is the rate at which the event occur in unit time. Lambda here is the rate at which the event occur in the unit time. For instance, if I'm having a class and I have 100 people in the class and the people are entering one by one, the rate at which they are entering per unit time, where unit time could be seconds or it will be minutes or an hour, depending upon what you are talking about. Are you getting? So a unit time, if I'm measuring the thing in seconds, a unit time will be seconds. If I'm interested in minutes, then the unit time will be minutes. If I'm interested in hours, then the unit time will be hours. So if, for instance, I'm interested in every minute, how many students enter every 1 minute interval. So that rate at which, the average rate at which students are entering every minute or unit time is what we call lambda. Or if you want to put in the general term, the average, the rate at which the event is occurring within the unit time is what we call lambda. Please, are we okay?
Yes.
Great. So let's look at a practical example. We finished with the mathematics. Let's now come to the statistics. A practical example. Let's start with question 1. Have you seen question 1?
Yes.
Yes.
Great. So we have this event. Let this event be a Poisson process with a rate of what? Lambda equals to 8. So we have lambda here to be equal to 8. So what does this lambda equal to 8 imply? It implies that the rate at which the event is occurring in unit time, per unit time, is equal to 8. So for instance, if you take the example I gave you, like the number of students entering every 1 minute, it's supposing 8 students enter every 1 minute.